Okay, well, welcome to you all here on this kind of dreek evening in Edinburgh. It's nice to see some familiar faces back from the last couple of years. This lecture course, Our Changing World, is an intimidating challenge for those who deliver the lectures, because it's a very unusual lecture course. Those who give these lectures are addressing three very different audiences. This course is an undergraduate course, a first-year undergraduate course here at the university, and in the audience there'll be students taking this as a course for credit. The audience also contains many members of the public who've braved the Edinburgh weather to be out here this evening, and a very warm welcome to all of you who've made it. And as I said, it's really nice to see some familiar faces here in the audience. But the third audience is the most intimidating of all, is the largest of all. This is the third year of this lecture series. So there have been so far 16 lectures in the last 2 years in the Our Changing World series. Those lectures, like this one, they've all been videoed, and the videos are available for anyone to see on YouTube, but also on the university's video site, which is iTunes U. So there have been 16 of these lectures in the past, and I can tell you that those 16 lectures have been downloaded around the world more than 500,000 times. So these lectures really have a truly global impact. So the success and the impact of these lectures has been such that the university is now launching a massive online course called Critical Thinking about Global Challenges. And that course will begin next January. Now this is a course where students, it'll be a wholly online course, it'll be free for those who register on it. So far that course has 30,000 enrolled students on it. So it won't begin until January. So I think that speaks to how the topics of this lecture course really touch on things that matter deeply to all of us. And of course the success is primarily it's a credit to the kind of enthusiasm, the commitment, the passion, and the quality of the communication of those who deliver the lectures. So Sandy, expectations are very high. I warmly welcome you, because the lecturer today is Professor Sandy Tudhope, who is the head... Yeah, Bill, please go ahead. Sandy is the head of the School of GeoSciences here at Edinburgh. So he's an Edinburgh boy himself. So he came to the university in 1988, but has a rather longer attachment to the city. And so being an Edinburgh boy, that probably explains why the passion in his life is coral reefs. So he's going to talk about coral reefs as kind of assays for climate change, and as this fragile ecosystem that is particularly vulnerable to climate change. So Sandy, warm welcome to you. We look forward to your lecture.
Thank you very much. It's certainly a pleasure to give the first lecture in this series. So I'm going to talk about tropical climate variability and change and its impact on some of the ecosystems, and in particular I'll look at coral reefs. But to start off with, I thought we'd go somewhere completely different, which is to the other end of the world. It's to the poles, and look at some evidence for climate change. So the ice sheets that grow in Antarctica and exist in Greenland accumulate gradually through time through the accumulation of snowfall. And it's possible to take cores down through them that go back through time as you go down, penetrating deeper into the ice. And in Antarctica, they've drilled down through the ice. They've drilled down more than 3 kilometers thickness through the ice. And that ice contains a record of past change. And so this slide is it's a magnified piece of ice shown in thin section. And it's pointing out that there's impurities in the ice that tell you about dust and salt and fire. There's the ice itself, which can be analyzed in terms of its chemical composition that can tell you about the temperature over the ice sheet when the snow fell. But there's also gas bubbles that get trapped in the ice. And these are trapping parts of the atmosphere that existed at the time that the ice formed. And so it provides a rather unique archive because you can therefore reconstruct the atmospheric composition back through time. And so this next slide, let's start off by looking along the bottom axis. This is time going from 400,000 years ago through to present. And this blue line, just focus on the bottom quarter of the figure, is a measure of the carbon dioxide concentration of gas in the bubbles in the ice of that age. And so here's the concentration, it's in parts per million by volume. And hopefully you can see that there's some variations in the carbon dioxide concentration in the ice through time. And it goes from about 180 parts per million to about 280 parts per million. And we get these big cycles that are about every 100,000 years or so. Well, we know that these changes in carbon dioxide coincide with the great ice ages that affected the Earth. And that during times of high carbon dioxide, like present, we have relatively small ice sheets. And during times of relatively low carbon dioxide, so for example 20,000 years ago, was the peak of the last ice age. At that time, global sea levels about 120 meters lower than present because so much water has been bound up in ice. So that's time. Not only did we have low carbon dioxide in the atmosphere, but global temperatures were about 5 degrees centigrade cooler than present. Now, these glacial interglacial cycles were not driven solely by changes in atmospheric carbon dioxide. We know that the trigger, the metronome, the pacemaker, was actually changes in the Earth's orbit around the Sun. But we do know that the changes in carbon dioxide in the atmosphere significantly amplified the climatic effects. And so they're responsible for about half of the temperature change that we see as we go from glacial to interglacial cycles. And as a geologist, I've had the benefit of looking further back in time as well, and I can say that it doesn't matter what time scale you look at. High carbon dioxide in the atmosphere coincides with high global temperatures. And it's for very well understood reasons. Carbon dioxide is a greenhouse gas, so it traps outgoing long-wave radiation in the Earth, and so it warms it up. So that's the history, that's the last 400,000 years, these natural cycles of carbon dioxide coinciding with natural changes in the Earth system as we go from glacial to interglacial cycles. So that's fine. Now, this is where we are, August, or where we were, August 2012. The atmospheric composition or concentration of carbon dioxide had gone up to 390 parts per million. This is higher than it's been for well over 1 million years, probably many millions of years. And the reason, of course, is that we're burning fossil fuel to support our industrialized world. This is where we're projected to get to. Now, there's some various assumptions in there, but we're very likely to get to around 700 parts per million in the atmosphere by 2100. Now, that will take us to higher concentrations of carbon dioxide in the atmosphere than we've seen for tens of millions of years. Now, it's not that we've never been there before. We've actually had thousands of parts per million carbon dioxide in the atmosphere before. So it's not like it's completely unheard of, but it's the rate of change that is quite remarkable. So what's going to happen then? We're putting carbon dioxide in the atmosphere. We know it's a greenhouse gas. Yes, the climate's going to change. And so here's a measure of global temperature. This is atmospheric temperature over the last 100 years, or from 1860 through to 2140 years. And you can see, in general, it's showing a rise in temperature, a little bit under 1 degree centigrade rise in temperature. Now, not only is the magnitude of rise, but also the pattern of rise, because you can see it's not just uniform, but it's got some plateaus and periods of fast change, is entirely consistent with our understanding of the climate system. So it's now gone to the stage where the scientists can say with confidence that we're seeing the effects of anthropogenic greenhouse warming. So that's how much we've warmed so far, and where are we going to go to? Well, that depends on a whole range of different assumptions that we must make. So here's time again. from 1800 AD, 2000, so we're just in here, and this is going out to 2100. And this is temperature change compared to 1800. And this grey shaded area is showing the range of global temperature change that is anticipated by 2100. Now you can see it's quite a wide range. It's somewhere between about 2 and 6 degrees centigrade. Now part of the reason for that uncertainty is because of uncertainties in the climate system. We don't fully understand it yet. But actually part of it is simply a function of what's the global population going to be? 9 billion, 12 billion, 15 billion? How much are we going to rely on fossil fuels to base our economies on? So there's assumptions in there that are actually much more to do with society than an understanding of climate. But it means that we've got quite a spread. So this is what you probably all know already. The world is warming. We've already seen evidence of this. By 2100, it's likely to have warmed by several degrees centigrade. So in other words, it's going to have warmed by 2100 by about the same amount as between an entire glacial to interglacial. Now, to get out of a glaciation to an interglacial takes about 10,000 years. We're going to do it in 100 years. That's what's quite special about it. Now, there's a lot hidden in that previous graph. Global temperature, that's what we tend to hear about, but of course it's not going to be uniform, the temperature change. It's much harder to predict how it's going to change spatially, but here's some estimates of how it'll change under 3 different scenarios, these scenarios being different rates of greenhouse gas emissions, different global populations. And on the left-hand side, you can see it's for the 2020s, and this is change compared to present day. And here's the 2090s change compared to the present day. And it's looking increasingly red as you go to the right, so increasingly warm. But you can see the high latitudes, and particularly the high northern latitudes, are predicted to warm an awful lot more than the tropics. And that's what we're seeing. We're seeing the Arctic becoming increasingly ice-free already. Now, of course, what impacts on people is not just temperature, but it's rainfall. And so if you look at, well, where's rainfall going? This is much harder to predict with certainty, but here's some estimates of changes in rainfall. And it's for the 2 seasons. This is our Northern Hemisphere winter, Northern Hemisphere summer. Basically in red, it's saying it's going to get drier. In blue, it's saying it's going to get wetter. And you can see that the drier areas are, where it's already very dry. It's the deserts. The deserts are going to get drier, and the wet tropics are going to get wetter. So that may present us with some problems, us being society. The other thing that we have to think about as well is that it's not just mean temperature or mean rainfall that's going to impact on us, it's climate variability. And as a general statement, global warming is likely to lead to increased extremes. So more floods and more droughts, and more heat waves and more cold snaps. So in general, we're anticipating a more extreme climate. Now, although change in the tropics, change in the high latitudes is likely to be more than change in the low latitudes, there's some really good reasons to look at the tropics in this context of global climate variability and change. If we look at the sea surface temperature of the ocean, and it's just color-coded so that red is warm and blue is cold, not surprisingly, the tropical oceans are very warm. And in fact, they're a heat engine that drives a lot of atmospheric circulation, and it certainly drives a lot of the moisture that ends up as rainfall. And it's small changes in the tropics that can have profound effects, not only within the tropics, but in the extratropics, because it's exporting heat through the atmosphere. And perhaps one of the best known aspects of this redistribution of energy and variability is something called El Nino, or the El Nino Southern Oscillation. This is, throughout much of the developed world, the man in the street knows about El Nino. It's quite remarkable. Let's, first of all, before we talk about the impacts of El Nino, say a little bit about what it is, what we know about it. So it's a climatic phenomenon that originates in the tropical Pacific, and it relates to a coupling between the ocean and the atmosphere. So let's look at what we would call a normal situation. It's a cutaway figure. So here's Northern Australia, Queensland here, here's Papua New Guinea, here's Central America, South America, Mexico. During normal conditions, you have strong trade winds blowing from the east to the west, and it's blowing the surface water, which is warming up in the tropics, towards the west. So you accumulate this very warm body of water here in the equatorial western Pacific. That warm body of water heats the atmosphere, it drives deep convection, you get huge thunderclouds that go up 10, 12 kilometers, you get very heavy rainfall. So that's what's shown here. So strong trade winds, very warm water here, and heavy rainfall. The thermocline marked on here is the depth in the ocean where you get a rapid change in temperature. So above the thermocline it's warm, below the thermocline it's cold. And so you can see that the thermocline is deep in the west, so you've got a thick layer of warm water, whereas in the east it's very shallow. And that's because the winds here are actually drawing cool, deeper water to the surface. Now, every few years, it's about every 3 to 5 years, this system breaks down and we get what are termed El Nino conditions. And in El Nino conditions, the trade winds slacken, so the warm body of water that was actually banked up here in the western equatorial Pacific, it was physically higher because the winds were keeping it there, it migrates to the central part of the Pacific and it takes the heavy rainfall with it. The thermocline in the west shallows, and the thermocline in the east deepens. This changes where you're injecting heat into the atmosphere. You're taking it from Indonesia, North Australia, Papua New Guinea, you're taking it here, and you're redistributing heat across the tropical Pacific. Now, you can ask, well, what drives this? Why does it occur every few years? And it's what's termed an auto-oscillation in the climate system. It's just a natural oscillation. Now, the concept of an auto-oscillation can seem a little bit obscure, but let's just imagine you're off on holiday and you're watching a palm frond in the breeze. And have you ever seen a palm frond kind of oscillating in a breeze like this? The wind's blowing onto it, it pushes it, then it flops back. Wind pushes it, it flops back. So the palm frond's busy oscillating. Now, the energy that's driving the oscillation is the wind, and the wind's not oscillating. It's just that the response is oscillating. And El Nino is a very similar phenomenon. It's energy from the sun that's driving the system, but the system is responding as an oscillation. And effectively what's happening is that during normal conditions, you're building up heat in the surface ocean until you reach some critical point when it becomes unstable, a bit like the palm frond, and then it releases back and it spills the heat out. So during an El Nino year, you get a global temperature anomaly because all this heat that was stored in the surface ocean is then released out to the atmosphere. So during big El Nino years, you get this, this energy released to the atmosphere. So we now understand the physics of this reasonably well. That's good. It has pretty much global impacts on weather. And so in this figure here, it's just showing in a cartoon sense the areas that get warmer, wetter, drier, cooler during the El Nino phase of this oscillation. It also impacts on intensity of cyclones, and it impacts on extreme events like floods and droughts. And the El Nino Southern Oscillation is responsible for very significant impacts. There was a very large one in 1997-98, and it's been estimated that it directly caused something in the region of 23,000 fatalities due to extreme weather events, and economic losses in the tens of billions of dollars. I mean, hard to estimate exactly. It's also appropriate to say that this is, people think of El Nino and they tend to think of it always as a negative. But what it's doing is it's changing the likelihood of getting storms or floods in different places. And in fact, if you're looking at it from a US point of view, an El Nino year tends to be a good year because it means that it's going to be a year in which you're going to get fewer tropical Atlantic hurricanes. So the damage and the deaths that are caused by Atlantic hurricanes are significantly reduced during an El Nino year. So the point here is that it's the variability that is the key. that large variability has significant impacts. Now the impacts, I'm not going to go into them in too much detail. I've mentioned that it causes floods and droughts and extreme storms. Tropical fires are associated with this, but it also has very significant human health impacts, so the distribution of diseases like cholera and typhoid, meningococcal meningitis, and others are quite tightly coupled. Dengue fever to this. Crop yields throughout the tropics and parts of the subtropics are tightly coupled to El Nino. So there's a lot of interest in, well, what's El Nino doing? How much does it vary naturally, and what's it going to do in the future? And this is a figure here that is a record of past El Nino activity over the last 100 years or so, again, going back to 1860. Now you can see it's a wiggly curve, but what that wiggly curve is measuring is it's measuring temperature anomalies in this part of the equatorial Pacific Ocean. And this is an area where during El Nino events you get positive temperature anomalies, so it's unusually warm. And that's what's shown as the shading in the background here. So red is meaning that it's unusually warm. So you can see that positive excursions on this curve relate to strong El Nino events. And so here's one very strong El Nino event in 1982-83, and here's another very strong one in 97-98. So this is a typical index used to measure ENSO strength. So you can see that not every ENSO event is equally strong. You can see that they occur every few years, but it's not like an absolutely regular cycle. And of course what I've done is I've drawn a blue line on, which happens to pick out that the two El Nino events in the 80s and 90s were the strongest of the last 150 years, and actually, based on old historical and documentary evidence, they're probably the strongest for several centuries at least. Of course, that begs the question, are these strong El Nino events a consequence of global warming? Are they a harbinger of much worse to come? So what can we do about El Nino prediction? How good are we at predicting ENSO? The next figure is going to show you predictions that were run during 97-98, and they started about here, but it's again looking at the same metric. It's using the temperature in this part of the tropical Pacific. So in blue is what actually happened to the temperature. And we're coming from January 97 97 through into late 97. And we're building into a big El Nino event. So in other words, this high point here is telling us that we're getting a very strong El Nino. Now these red lines coming out here were predictions that were done with climate models at this point here. So the predictions were made in February. And you can see that they actually predicted that we were going to build into an El Nino event, but that the predictions started to tail off in their skill after about 6 months in. And this figure is just showing a general conclusion that we could bring, which is that although we've now got climate models which capture the essential physics of the El Nino phenomenon, they can reproduce it, they can only give us predictive skill about 6 months ahead, and beyond that they can't. So they will not be able to tell you what's going to happen a year, 2 years ahead. So in other words, you've got limited predictive capability. Now the other question, of course, is with greenhouse warming, as we increase greenhouse gases, what about using the climate models that we're using to estimate future climate and explicitly look at El Nino in these climate models and see what happens when we double atmospheric carbon dioxide, for example, as we go from the pre-industrial 280 parts per million up to 560 or out to 700 parts per million. And let me talk you through this one. There's an awful lot of work went into this, not by me, I should hasten to add. But what we've got here is, on this axis here, it's saying whether or not in future the tropical Pacific Ocean is going to be more El Nino-like, which just simply means slightly warmer in the center and not as warm in the west. So that's probably of less interest. But then on this axis, it's whether or not the strength of El Nino variability is going to increase, which is up, or decrease, which is down. And this is for future climate. And then shown in the different colors and symbols with their little error bars are all the climate models that are being used by the different world centers for future climate predictions. So although all these models will agree that global climate is going to warm, they'll all agree that it's going to warm by about the same amount, you can see about half of them say that El Nino is going to strengthen, and half of them say it's going to weaken. So where we're at just now is we don't actually have any skill at all. We've got no confidence at all in saying what's going to happen to El Nino in the future. And that's a shame, because the societal impacts of a change in the strength of El Nino would be enormous. So I'm now going to kind of divert off a little bit down a research angle, which is looking at one particular style of research that's being done to try to help address this question. And I'll warn you now, it hasn't reached a conclusion, so it hasn't solved it, but hopefully you'll see where it's going. So one of the issues just now is that the instrumental record of past climate is not long enough for us to know whether El Nino changes a lot naturally. What's the sort of natural range of variability, and does it change if you change global climate in a predictable way? Because we've only got instrumental records back 100 years at the most, and through most of the tropics back just a few decades. So this causes us to have to look for alternative ways of finding out about past climate. And so just in the same way that we used ice cores, you can actually try to find archives in the tropics. And one of the best archives to use for this kind of work is in the tropical oceans, where ENSO originates, and it's the skeletons of annually banded massive corals. These are dome-shaped corals that are growing upwards and outwards. They're laying down a skeleton of lime. They're growing at about 1 centimeter a year, and so a coral like the one illustrated here is of the order of 100 years old. If you take a core down through its skeleton, you can see different types of annual rings in it, just depending on how you look at it. On this side it's illuminated under ultraviolet light. This is a density banding illustrated by taking an X-ray, the same as you'd get an X-ray to look at your body. So you can get annual bands, so you can see how much the coral grew each year of its life, and you can count the bands backwards and get a record of the growth of that coral. Now, if you're to summarize some of the attributes of these corals for this kind of work, it's that they're relatively abundant through the tropical oceans, so you can get some spatial coverage. A key thing is that in the chemistry of their skeletons, they record information about the temperature of the water they're living in, but also its salinity, how salty it is, and that tells you something about the amount of rainfall at that site. Individual colonies can live for a few hundred years. I've mentioned before that they grow relatively fast, between 5 and 20 millimeters a year, and so that means that you can get records with about a month's resolution going back centuries with an individual coral. But also, if you can find old dead corals, they're very easily dated by radiocarbon, but also by another technique which is more precise, or accurate, which is uranium series dating. So you can extend these records back thousands of years. Here's an illustration of a coral record shown in red against temperature measured in this box of the tropical Pacific. It's called the Nino 3.4 box. It's an area where it gets very warm during an El Nino event. And so in blue is the instrumental record, just from 1950 through to 2000. And in red is a record that's derived from analyzing the composition of the coral skeleton. In this case, we've analyzed the oxygen isotopic composition, and here it's responding to temperature. And so you can see that you can actually very faithfully record temperature, even over that large piece of ocean, just from a single coral. So that's like a proof of concept. It shows that it works for a living coral. You're comparing it with instrumental records. That allows you to kind of calibrate what you're doing. And then you go and look for old dead corals. And so here's an area of the world where the land's going up because the plates are colliding. It's Papua New Guinea. And you can see along the coast here, you've got where the waves are breaking, there's fringing reefs growing there. And every now and then there's a big earthquake and the reefs get lifted out of the water. Another earthquake, they get lifted out. And so as you go inland, you see these terraces, and these relate to former reefs. In fact, up here are reefs that grew about 125,000 years ago during the last interglacial. That's the last time the Earth was kind of as warm as it is. And in between then and now was a glacial. And so you can get access to these old dead corals. So there's one that's been lifted out a few thousand years ago. You can collect cores down through the skeleton, you can date them, and you can reconstruct the climate. Now what we're trying to do here is we're going to regions where the climate is very sensitive to El Nino, and we're going to try to use the analysis of these corals to see whether or not El Nino has changed in the past. Has it always been the same as we see the last century, or are there times when it's stronger and times when it's weaker? And can we understand what the drivers might be? So there's a lot of data here, and I did produce some of this, and this did take me a long time along with many colleagues. On the left-hand side, we can go through this fairly quickly. We've got a series of records from corals. Along on the x-axis, we've got time. So the top one is a modern coral. It's going from 1880 through to 2000. And so the coral's been analysed at about monthly resolution, and you can see that red curve wiggles around. That's the seasonal cycle, and it's also interannual variability, which relates to the strength of El Nino. These blue ones are from fossil corals, going back in time. The ages here, this is about 10,000 years old, about 9,000 years old, about 6,000, 3,000, and 2,500 years old. So these are just little windows into climate at these times. You're ranging from like 50 years long to 100 years long windows. And hopefully you can see, just even looking at the left, that there's a lot less variability in these older corals than there is in the modern one. And if you filter the corals specifically to look at the strength of El Nino as it's manifested in these corals, you can see that El Nino at the present day is much stronger than El Nino 8 or 9 or 10,000 years ago. So what we're then able to do is we're then able to use the climate models that are used for future climate predictions. We then run them for this period 10,000 years ago. And well, what was different 10,000 years ago? Well, atmospheric carbon dioxide was pretty similar to the present day. And in fact, the main difference at that time, we just got the residue of the big ice sheets. They were just finishing melting. But the big difference was that the Earth's orbit around the sun was slightly different. The nature of seasonality was a little bit different on Earth. And so you can drive your climate model with these changes in seasonality, and you can see what result you get. So in the top, we've got our modern coral. That's modern ENSO. That's our benchmark. And here's the fossil corals. That's a much reduced strength of ENSO. And we're saying that it's reduced by about 80% if you're discussing the parameter variance. Here's a climate model run for modern. Again, the wiggles up and down are the model ENSO. And here's the model then run for 6,000 years ago. It has got a reduction in ENSO, but it's much, much smaller than we're seeing in the coral data. So what this allows us to do is it allows us to see which models appear to have the most skill running backwards through time, because they may be more reliable running forward. Or certainly, put it this way, if a model doesn't perform going backwards through time, then you know that you wouldn't necessarily trust it going forward through time. Now obviously it's very different. The changes in seasonality that probably drove these changes in the strength of ENSO in the past are very different to the changes in atmospheric composition, the CO2 in the atmosphere, that's going to drive change in the future. So you can't draw straight analogies, but what I would say is that the evidence from the past is that ENSO is sensitive, probably very sensitive, to aspects of global climate change. And therefore it should not be a surprise to us if the strength of ENSO changed in the future. As I say, this research is just ongoing and we can't draw any firm conclusions from it. So for the last few minutes we were talking about using corals to reconstruct the past and using them then to try to ground truth our estimates of future climate change. And certainly that's one way you can do it. You can use them as archives of past change. But let's turn it round and think about the corals and the coral reefs in the context of the climate change that's coming and what's going to happen to them and what do we know and what don't we know about that. So corals, the kind of corals we're talking about here are the shallow water tropical corals. They're scleractinian corals. And they evolved around 250 million years ago. So they've been around in the Earth system for quite some time. They're colonial animals. If you take a close-up of the surface of one of these corals, you can see a whole set of individuals. Each is called a polyp. It's got tentacles, it's got a mouth, it can forage, it can feed, and it can translocate energy from one polyp to another. They're all genetically identical. And if you were to go and tickle a polyp at one end of the colony, you can see the message rippling through the colony and they all duck back down inside the skeleton. So it's a colonial animal. Interesting sort of phenomenon. Now I've mentioned that they can feed, and they do. They capture zooplankton and probably phytoplankton as well. So they do ingest food. They are animals after all. But actually they owe their success, their remarkable success, to something that you can see if I go back a slide. Sorry. If you take a close-up view of these tentacles here, you can see in there these little brown blobs. And if you take an even closer up view, that's what they look like. And these are single-celled algal cells. Sorry, they're algal cells. They're dinoflagellates. They're a symbiotic algae that lives inside the coral tissue. And the algae are photosynthesizing, so they're fixing carbon. And that fixed carbon gives energy to the coral, allowing it actually to grow much faster than it could do if it was simply foraging. And in return, the algae get protection because the coral has got stinging cells, and it itself is not terribly palatable, so not many things will graze a coral, so the algae get protected. And also they get the waste products from the respiration from the coral, so they get nutrients and other waste products, the CO2 from the coral. So a symbiosis, both do well out of it. But it's because of these algal symbionts that the corals are able to grow so fast, and that's the reason why these shallow water reefs are restricted to shallow water. Now, they're also tropical, by and large, and here's a distribution of corals, about 800 species of corals, and you can see that the center of diversity is here in the Indo-Pacific, but you also get significant numbers in the rest of the Indian Ocean and in the Caribbean Atlantic. And coral reefs are remarkable. They occupy less than 0.1% of the ocean, and yet they're one of the most diverse ecosystems. There's over 800 species of corals. There's over 4,000 species of fish. There's estimated to be somewhere between 1 and 9 million organisms that are reef specialists that have evolved to live in reefs. So they're very much the marine equivalents of a tropical rainforest. They have this phenomenal biodiversity. And for that reason, they are important ecologically, but also they have got very important side effects, if you like, or services that they're providing to humanity. They build these phenomenal structure. Okay, it's built primarily by the corals laying down their skeletons on top of one another, but there's all this biodiversity around about it. There's more than 1 billion people in Asia that depend on coral reefs for nutrition. They provide targets for tourism. They provide coastal defense. They provide building materials. It's been estimated that coral reefs are of the order of $400 billion worth of services provided to mankind each year. And even that is likely to be an underestimate in terms of if you didn't have them, how much would you have to pay to get the equivalent service? So they are very important for us, as well as just intrinsically for their own right. Now, coral reefs are under quite a lot of pressure from a number of direct effects, and we could have an entire lecture series on the direct effects on corals. Things like overfishing, land use change, dredging, direct impacts that will cause reefs to decline. And there's plenty of examples in heavily populated areas where the reefs have transformed from their vibrant natural selves into shadows of their former selves. But there are still parts of the world where there are reefs that are pretty much pristine. If you go out into the central part of the Pacific with low population densities, you can see reefs as they should be. What I'd like to talk about here is not the direct impacts, but actually the indirect impacts of man's activities. And one of them is it's the temperature change. Most corals live very close to their upper temperature tolerance. So although corals like living in the tropics, they like warm water, if you take a coral more than about 1 degree centigrade warmer than it usually gets in an annual cycle, the relationship between the coral and the algal symbionts breaks down, and the algae either die and go away, or they get ejected from the coral. And the coral is then bleached because it's the algal symbionts that give it the color. So this coral here is alive, but the tissue now is translucent. It's just the animal tissue there. It's got no algae. And it's been bleached because it got warm. This is in Thailand, and it got warm for a month, and this is what happened. Now, in this state, the coral is critically weakened. If the temperature drops back down, the algae can recolonize and the coral can recover. But in many cases, once a coral's bleached, it goes on to die. So during the 1997-98 El Nino, about 16% of the world's coral reefs suffered mass mortality as a consequence of the elevated temperature associated with that single El Nino event and the consequent coral bleaching. So, you can see probably where this is going. If corals are living close to their upper temperature tolerance thresholds and we're warming the world, what's going to happen to coral bleaching? What's going to happen to corals? Well, you can do a pretty simple back-of-the-envelope style calculation. And this is based on climate model output for Tahiti. Here, it's actually historical records from 1850 through to present, then model output from present on to 2100. And you can see that it's suggesting that Tahiti is going to warm. Okay, it's going to warm like the rest of the planet's going to warm. Now, shown in the solid line here is the temperature at which corals in Tahiti currently bleach. So if you exceed that temperature, they bleach. And if that bleaching persists, they go on to die. So it doesn't look too good, does it? It suggests that by about 2020, corals are going to be bleaching most years. Certainly by 2050, they're bleaching most years. And by 2100, well, surely they're gone. But this presupposes that corals will have no ability to adapt or to acclimatize. Now, on some time scale, we know that they can adapt or acclimatize. So if we go and look at the same species of coral and we look at it geographically, we can find that its bleaching threshold varies very significantly. So maybe in the Persian Gulf it will tolerate 35 degrees centigrade, but in the southern Great Barrier Reef it'll bleach at 24 degrees centigrade. So that's what's shown on that left-hand side. It's the kind of range. Actually, they never bleach at 24, but say between 27 and 34 would be that range. Now, clearly these corals have been able to adapt, most likely genetically adapt to these environments. And the question really is, what's going to happen in the future? And that's where a lot of work is being done to try and assess this. There's the obvious experiment you can do. You can take a coral, you can put it into a tank, you can heat up the tank and see what happens to the coral, but that's just a short-term experiment. We kind of know the answer there, it's going to bleach. But people are now doing much more subtle experiments where they're doing experiments over many years, so they very gradually increase the temperature to see what the response of the corals are. There's an additional element to this, which is, I'm talking about corals, but actually it's the coral-algal symbiosis that's really important. And it turns out that there isn't just one species of algal symbiont, these little single-celled algae, but there are several different species, and these have got different temperature tolerances. And so there's a possibility that the corals will be able to swap temperature-intolerant symbionts for temperature-tolerant symbionts. There's some evidence that this is happening naturally. There's also a possibility, because of the turnover time of an algal symbiont is likely weeks as opposed to the generation time for a coral being decades. Well, you've got thousands of opportunities for genetic adaptation of the algal symbiont, so that's the weak link in the chain, whereas you don't have many generation times of the corals if that's what's got to genetically evolve. So there's a lot of work going on the genetic side to try and predict. And basically it's trying to see, is this what's going to happen? Will corals or their symbionts adapt or acclimatize such that actually there's not too big an issue? They manage to do it fast enough in relation to climate change. Or is it going to be something like that where they get part way there but they don't quite get there, in which case the future of the corals is looking very bleak? Or it could be actually that you chronically stress the corals to the extent that any ability to adapt or acclimatize is actually weakened, and you go the other way, and you go across some threshold and they just plummet. And actually, to be honest, we don't know where we're going yet on this. ocean acidification. I'm sure you've all heard about this. This is the other insidious threat to coral reefs and actually many organisms that make skeletons of lime in the oceans. As we put carbon dioxide into the atmosphere, some of that carbon dioxide dissolves in the surface ocean. There's actually some quite complex chemistry going on, but in effect, as you dissolve carbon dioxide in the ocean, it combines with water, it forms carbonic acid, so you get hydrogen ions and bicarbonate. The hydrogen ions then attach onto existing carbonate ions, that's the CO3 2- to form more bicarbonate. I went through that a bit quickly, but the net effect, what you have to remember is if you dissolve carbon dioxide in the ocean, you will increase the number of the proportion of hydrogen ions, that's making it more acidic, but also you're decreasing the concentration of carbonate ions that are dissolved in seawater. If it's the carbonate ion concentration that dictates how soluble the carbonate minerals are. So the corals are making their skeleton out of a form of lime, it's calcium carbonate, it's the mineral aragonite. Well, the solubility of that aragonite depends on the carbonate concentration in the seawater. And the more carbon dioxide you dissolve in that seawater, the more soluble their aragonite skeletons become. So the harder it becomes for them to precipitate lime. And so that's what ocean acidification is. It's meaning that it becomes harder and harder to precipitate, grow a lime skeleton. And here's some projections of the saturation state, which we could just simplify by saying, how easy is it to grow a skeleton of aragonite, the mineral that the corals grow their skeletons from, in the year 1865. So this is based on modeling, so it's basically pre-industrial. Then the year 2065. And red colors mean that it's really easy to precipitate a skeleton. And as you get into the bluer colors, it means that you're less supersaturated, and so potentially it's harder to grow a skeleton. So if you took this at face value, you'd say it seems likely that corals will decrease in their ability to grow skeletons. Now this could seem really catastrophic, especially if you combine it with temperature change, but I would emphasize that the surface ocean is still super saturated with respect to aragonite, even at 2100, even under bleak scenarios. So actually it's not quite as obvious as it would seem, because on the surface of it, the corals might well be able to overcome this difficulty. Now, having said that, there's a whole set of experiments being done where people have taken corals, they've put them into tanks, they've bubbled CO2 through the water or similarly manipulated the water composition, and they've seen how the coral growth rate has changed as a function of the amount of carbon dioxide that you bubble through the water. So it's simulating future climate change. And this is the aragonite saturation state. So this is basically how much CO2 you bubble, with more CO2 bubbled as you go to the right. And this is the percent of pre-industrial calcification rate. In other words, as you come down here, you're decreasing your calcification rate. And what was interesting about this compilation that's done by a colleague in Miami is that if you take all the experiments and just plot them up, it looks like there's a sort of linear response, that as you dissolve CO2 in water, the growth rate of the corals decreases linearly by about 16%, covered there, 28% reduction in calcification rate for every unit reduction in saturation state. So that looks rather bleak. Now, is there any evidence that this has actually happened? Because we've been putting CO2 in the atmosphere for a long time, since the start of the Industrial Revolution. So if this is true, we should be seeing corals reducing growth rate certainly from 1850 onwards. Well, here's some evidence from the Great Barrier Reef, a very large study that was done there, looking at growth rates of corals back through time using the annual bands in some of these massive corals, and looking at their growth rates. A huge study, the length and breadth of the reef, and indeed it does show a rather catastrophic decline, or very large decline, catastrophic's too strong, in growth rate since about 1990. And in fact, a similar study that I was involved with in Thailand over the same time period showed a very similar decline in growth rate. So that doesn't look good, because that is in line with what you'd predict. But then, wait a minute. If this was driven by changes in atmospheric CO2, why are the coral growth rates, this is the calcification rate, this is the extension rate, they're related, why are they basically increasing up till 1990? That's not what we would have anticipated from the CO2 effect at all. And so I think what it's pointing to is we don't fully understand these systems yet. Of course, we could hypothesize that what's happened here is that we are gradually warming, the corals were coping with it. In fact, if you warm very gently, corals do grow faster. But that we've reached some tipping point where the corals are feeling the dual effects of the stress of increasing carbon dioxide in the atmosphere and increasing temperature, pushing them towards their bleaching thresholds. And suddenly they've crossed that threshold and now they're crashing. The answer is, well, we don't know whether or not that is the case. There's now other studies going on in different areas of the world to see if this is a general situation where corals are decreasing their growth rate. Another thing that you can do is you can try to find natural analogues. And this is very useful because you get round the time dimension. And this is a place in Papua New Guinea, which is a volcanically active area, and it's where there's a natural CO2 seep, carbon dioxide seep from volcanic activity into a reef environment. And so what the researchers here were able to do was they were able to go to corals that are far away from the seep, look at their growth rates, look at the community composition, the diversity, etc., then gradually work their way towards the seep and see what happened. And on the left-hand side, you're seeing the situation which is the control situation, well away from the seep, a typical diverse reef with high species diversity. And on the right-hand side, we find that even quite close to the seep, with a lot of CO2, with relatively acidic conditions that would simulate 2100, you've still got quite a lot of coral there, but your diversity is plummeted. You're only getting a few species. And really interesting, the corals that do survive are growing as fast there as they are away from the seep. So again, it's pointing to the corals themselves having some ability to regulate. So the short-term experiments that you can do by taking organisms, putting them into tanks and simulating the future don't always play out in the same way as occurs if you've got time. And that's where I think some of the real challenges lie in this field, is coming up with experiments that allow you to uniquely test the response of corals on timescales. So, as a summing up, it's really clear now that the globe's climate is changing. The tropics will change, not by as much as the high latitudes, but the changes will impact on many more people because most of the world's population lives in the tropics. And it's also where you have a lot of the poorest world population. We don't know whether climate variability like El Nino is going to increase or reduce. If it changes, it will have a very significant impact on people, but it could also have an impact on ecosystems, because a big increase in El Nino could change, for example, the incidence of bleaching in its own right. And in terms then of the impacts of climate change on reefs, it's very hard to know exactly what's going to happen, but I would bet that reefs are going to change a lot. So I wouldn't go for the catastrophe, I don't think we can say that, but I think there is going to be some fundamental changes there. And there's some real, there's some opportunities and requirements for some very innovative science over the next decade to try to understand more clearly exactly how natural systems like reefs will respond to climate change. So thank you very much.
Thanks very much, Sandy, for that kind of wonderful introduction to the series of lectures. I'm particularly kind of taken by the way that your lecture was really kind of exemplified the nature of science, and that you really stressed the limits of our certain knowledge and the boundaries of our current understanding, and actually the interesting, the exciting parts of science are in these areas of the unknown, where we're much less certain and really quite unclear about what's going to happen in the future. And I think it's kind of very valuable to kick off recognizing that science is about the limits of our understanding and about the uncertainty beyond those limits. So thanks for that. But there are some questions that for me you didn't resolve. I mean, and I wonder if there's any kind of evidence for changing kind of geographical range of the corals, and how much fossil fuels we've got to burn to see them up here in Edinburgh.
Well, unfortunately, the likelihood is that as you increase the temperatures, you could imagine that the range of corals will increase. So as you say, you could imagine that corals will spread to higher latitudes. But at the same time, the water is getting more acidic, and the effects of that ocean acidification are particularly chronic in colder water. So actually, although we will see some range changes, they're not going to spread too far, I don't think.
All right. That's
Sorry.
right. Can I see what questions there are from the audience? So it's up to you. We have a roving mic, so if anybody's got any.
Are there any similar studies on the cold water corals off the west coast of Scotland and like to be able to compare against these ones?
Yes, that's a great question. And yes, there are. So cold water corals are also scleractinian corals, but they don't have algal symbionts. And so they're able to live in deeper water. And if you were talking, say, 20 years ago, they were thought of almost as an oddity. They came up in trawl nets every now and then. A few scientists would pick them up in dredges. But now that people have started to look for them, they find, as you probably know, that they're much more widespread than we had previously known, particularly in water depths of a few hundred meters to about 1 kilometer's water depth, so along the shelf edge and upper parts of the slope. So they are there in high abundance. They're a very diverse deep sea ecosystem, and they too are under very significant threat. And in particular, it's because the water they live in is cold, so the effects of the ocean acidification are likely to be felt even sooner. So in the same way that people are doing experiments with tropical corals, people are doing experiments with some of these deep sea corals. And in fact, some of our colleagues at Heriot-Watt University have got a fantastic aquarium set up where they're manipulating the environment, so they're able to culture these corals and seeing how the corals can cope with different temperature and CO2 conditions. So yes, directly analogous.
I was wondering what causes the annual bands to form in the corals, because in tree species you don't really get tree rings in tropical environments because there's no seasonality, or not so much. So, yeah. Yeah,
good question. So, let's start with trees. Yes, in mid-latitude trees, the reason you get annual bands is because the tree shuts down during winter. So you've got a growth season and a non-growth season, so you pick up a couplet of bands. It's the kind of early wood, which is fast growing, then the late wood as it turns to shut down. And in the tropics, most trees don't have annual bands because even if there's seasonality, the trees manage to grow year-round. But there is, in most parts of the tropic, there is seasonality. And that seasonality is usually in temperature or rainfall, or both. And so these environmental effects can influence the growth of the coral. So different types of banding. The two types of banding that I illustrated graphically there, one was visible under ultraviolet light, and that's actually due to organic compounds that have washed in from adjacent land masses that are naturally fluorescent. And so if you have heavy rainfall, you're washing they're humic acids into the adjacent water, seawater, and they're passively then getting incorporated into the coral skeleton. So there you're picking up changes in the rainfall or the runoff from the adjacent landmass. In the case of density banding, it's usually changes in the temperature that influences the density of the skeleton that the coral lays down, so it's simply recording that.
There's a huge amount of information present in these bands, in fact.
Yes, I didn't really touch on the different tracers that are used. We tend to use isotopic tracers, particularly the oxygen isotopic composition of the skeleton, because that turns out to be a very faithful recorder of changes in the temperature of the water that the coral lives in. The only disadvantage of using the oxygen isotopic composition is that it also responds to changes in rainfall. So isotopes of oxygen are different forms of oxygen which have got a different mass. They've got different numbers of neutrons. And The oxygen 18 tends not to be evaporated as much as oxygen 16. And so rainfall tends to be isotopically light. So during periods of heavy rainfall, you end up with more oxygen 16 compared to 18 in the surface ocean. That gets incorporated into the skeleton. So the corals, to some extent, then get a mixed signal of temperature and rainfall. So there's other tracers within the skeleton. In particular, there's some elements that are incorporated, apparently driven primarily by temperature. So for example, strontium, the element strontium, can substitute into the crystal lattice in place of calcium, and the degree to which it substitutes in is a function of the temperature of the water. So what you try to do is you combine a number of different tracers to isolate temperature effects versus rainfall effects.
So it's the strontium index that you use to reconstruct the historical record going back in time from the...
Well, there's both strontium and the oxygen. The oxygen's actually easier to measure, and it turns out that it's actually remarkably robust because in most places the temperature and the rainfall coincide.
And we know they're stable and reliable even going back into fossil history.
Good. So the fidelity of the records as you go back through time. It's certainly something that you have to assess, because these skeletons, if you leave them for millions of years, will recrystallize. So the older they are, the more prone they are to having recrystallized. Now, fortunately, there are some really distinctive signs of recrystallization. They actually change to a different mineral. There's some other features of changes in crystal structure that you can detect. But yes, in this talk I was skimming over it like it's easy to find fossil corals and they're all perfectly preserved and they all give you the ideal records of past El Nino activity. The reality is that it's very hard to find well-preserved corals that are more than 100,000 years old. And so I'd say that we've got a reasonably good impression of El Nino activity on that kind of time scale, but finding them, say, 1 million years old or 10 million years old is a challenge.
Okay, you've already mentioned the dual effects of global warming and ocean acidification on coral reefs, but this is probably quite a simple question, but how does global warming affect the ocean acidification process itself?
The main effect is, if you're talking about warming, so the anthropogenic change, obviously there's the CO2, carbon dioxide goes into the atmosphere, it dissolves in the ocean, that's giving you ocean acidification. If you look at just warming, then the warmer the water, the less soluble the carbonate minerals. So to some extent, as you warm, if you weren't adding carbon dioxide in at the same time, you'd make it easier for corals to grow. And that's probably why, if you look at the present day at the growth rate of corals as a function of the temperature of water they live in, so if you go along, for example, the Great Barrier Reef, and you go from the northern Great Barrier Reef at 29 degrees centigrade to the southern Great Barrier Reef at 24 degrees centigrade, and you take the same species of coral and you plot its growth rate, you see that that shows a strong correlation with temperature. And that's probably a function of this solubility effect. Does that answer your question? Because they're kind of competing against one another, if you like. Yeah. And I should just emphasize again, if you were to very gradually increase temperature, corals would probably like it. They would grow faster. The bleaching issue is when you take them to a temperature that they've not experienced within their lifetime or within their several generations' lifetime. That's what we don't know.
I think we should perhaps wrap it up there, just to thank you very much. I can see that the audience here is looking at you with sullen envy, thinking that you kind of, it's a tough job going out around this coral reefs, but somebody's got to do it, and they just wish it wasn't you, but it was them. But I'm sure that we're all very thankful for your lecture. It's fascinating, so thank you very much.
You're welcome.
This production is brought to you by the University of Edinburgh.